So good afternoon, everyone. I'm Nathaniel, this is Kieran, and this is Curtis, and we are the Magjig design team. And today we'd like to talk to you about the magnetic jig design, our proposed solution to a problem that was suggested to us by the Canadian Light Source. And this is what we've been working on for the past 2 terms. So to outline the presentation, we'll begin with a background motivation for the problem. Then we'll look at the problem definition. We'll then talk about how we tackle the problem, a search for a sufficient magnetic design, and then we'll present to you our final magnetic design as well as the mechanical system, and end with a discussion about anticipated future work. So background and motivation. The Canadian Light Source is the only synchrotron facility within Canada, and it promotes research in a variety of different fields, including health, agriculture, materials science, and many more. And as a result, it has an important role. So being a synchrotron facility, it requires magnetic devices. These are also called insertion devices in order to operate. And accurately measuring the magnetic fields produced by these insertion devices is, as a result, very important. And for accurate measurement of these magnetic fields, the precise location of the magnetic field sensor, in this case a Hall probe, with respect to this insertion device must be known. So what this is saying is that we want to know exactly where we're measuring the magnetic field. And this is very important because when they install these insertion devices into the synchrotron, if they're misaligned slightly, if we're measuring the magnetic field in the wrong location, it can actually take a lot of time to realign these. So the Hall probe itself is composed of 3 sensors, and this allows it to measure the magnetic field in 3 spatial axes. So you can see from this little diagram here, I guess kind of far away for some of you, but there's an X, Y, and Z sensor mounted onto a plate. And as a basis, location of these 3 sensors is specified to an accuracy of 50 micrometers by the manufacturer. And our design problem is to determine the location of the Hall probe sensors to within 10 micrometers. So how to tackle this problem? Well, a device is required, and we call it a magnetic jig. So this magnetic jig must have 2 main functions. Number 1, it must produce a magnetic field with distinct field features for each Hall probe sensor and in each axis. And what this means is that it allows us to relate the position of the Hall probe sensor itself to the magnetic jig. And then its other function must be that it should accommodate ball-mounted retroreflectors to allow the determination of the location of the magnetic jig with respect to the insertion device. And Kieran here will actually talk about that more later when we talk about the mechanical system. But what I want you to get from this is that this allows the magnetic Hall probe sensor itself to be related to the insertion device. So let's talk more about field features and how these allow us to determine the position of the Hall probe sensors. These are typical field features that we're looking for. So on the left here, we have the magnetic field measured by the X sensor with respect to X, Y, and Z position. And we have the same for the Y sensor and the Z sensor. So ultimately, we're looking for 9 full plots of field features that we can use. Now, you may have noticed that these 2 here, if you can see it, actually have very low magnitudes. And one of our constraints is that we have to have at least 50 Gauss minimum peak field magnitudes. So this is one of the constraints that makes this design a little bit harder. So these fields we won't be able to use. So from the remaining fields that we have from these typical field features, you can see that in red we have these peak fields. So it's just a peak, as the name suggests. And basically, we would move the Hall probe up to find a maximum value. And then in green, we have these zero crossings, where the trace actually crosses the axis itself so that we can find a sign change. So how would we use these field features to determine the Hall probe sensor's location? Well, here's a picture of a Hall probe sensor, a Hall probe itself, and we have 3 sensors. Now, in this particular case, we want to find the X sensor's location along the X-axis. So on the right here, we have a picture of the magnetic field measured by this X sensor. So as we scan across this magnetic jig, we can see that the X sensor magnetic field that it's measuring actually varies as a peak. So if we can align it to the peak value, we can determine the X sensor location as being at X equals 0 with respect to the magnetic jig. And this also has a constraint that we have to have at least 20 Gauss per millimeter over a 1 millimeter range. And here's another field feature. This time we want to find the Y sensor's position along the X-axis. We do the same, but this time we have a zero crossing. So the measurement of the magnetic field for the Y sensor has to change sign for us to know that the Y sensor, represented by the red cross, is at the center point. And again, we have the same constraint. So now I'll pass it on to Curtis to talk about the magnetic system.
All right, so this is the CLS's current solution that they have. It functions theoretically. So what that means is that within our magnetostatics code, it produces the 9 plots that are required. However, the reason why it doesn't work in practice is because these 2 points have to be aligned very precisely, and the machine tolerances of the mechanical system just doesn't allow for this. So as far as our design process for our magnetic system goes, it was essentially just trial and error within that magnetostatic software. So we coded up a number of different geometries and applied a number of different magnetizations to these geometries, and we saw what effect it had. We saw if we had 9 plots that worked for us or not. If it did give us 9 plots that worked, then we would have to optimize the system to see if we could actually attain those constraints that Nathaniel talked about earlier. So for our selection, it came down to these 2. And that was because these were the only 2 that satisfied our constraints of field peak and zero crossing strength. So originally we thought this was going to be our final design. That was before we came up with this. But there was a major flaw with this system, and it was that it was very susceptible to differences between these 2 magnets. So if one was very slightly stronger than another, then we would have very bad effects on the plots, and we wouldn't be able to calibrate our Hall probe. But noting this error, we came up with this single component system. So the reason why a single component is very good is because it doesn't have to be aligned to another magnet, and it doesn't have to be exactly the same magnetization-wise as another magnet. So our final design that we chose for the magnetic system was this diametrically magnetized ring, and as you can see here, we get all 9 plots that we require, so either zero crossings or peaks. When it's magnetized in the X direction, we get these blue plots, and when you rotate it 90 degrees, so our mechanical system is going to require to rotate the magnet 90 degrees, we get these red plots. So again, the big problem with the old jig that the CLS was using was the machine inaccuracies. So the ones that we looked at that we were concerned about with this magnetic design was rotation in all 3 directions. And this just shows the effect of one of those rotations, the Z rotation actually. And as you can see, the zero crossing point changes slightly, so that's bad. We can't use this. So we need to analyze these rotational errors now so that we can determine how accurate our mechanical system has to be. So the way we did that was with a number of these plots. What this shows is the effect of Z rotation on one of the traces of one of the plots. So one of these lines on one of these plots, so this is just one plot, I guess. And on the x-axis, we have the rotation with respect to the Hall probe in degrees, and on the y-axis, we have the location shift. So that just kind of shows the effect. So from many plots like that, we basically came to the conclusion that in order to achieve an accuracy of only 2 micrometer shift in those field peak locations, we would need in the Z direction about 175ths of a degree, and in the X and Y about 120th of a degree. So when we design our mechanical system now, that's what we're aiming for. That's the accuracy we're aiming for.
Okay, so moving on to our mechanical system, we did this under the advice of the CLS after they rather liked our initial ring magnet design. And what the idea was is that we have the ring magnet held inside this holder via an interference fit. In other words, the radius of the magnet holder, it matches the outer radius of the magnet and is able to fit together via friction. Now this holder is then held inside of this frame, which is supported by these tooling balls and these tooling ball holder mounts. And what this allows is that because it's only held in lightly by its own gravitational force, is that it allows us to pick it up and rotate by 90-degree increments in order to get the rotation that we desire. Now, in order to position the holder, we have to use what are called ball-mounted retroreflectors. Now, what these are is that this works by simply firing the laser into the retroreflector, which then uses a series of mirrors, which then reflect the laser back to a detector, which can then figure out exactly where they are specifically in three-dimensional space, and thus figure out where the magnet is. Also, another thing about this frame is that it allows the holder to be rotated by 90-degree increments in all axes, which allows us to do a symmetrical analysis of the magnet, and thus determine if there's any offset errors in the system. Now, to account for any tolerances, what we've done is that we've positioned everything on top of this tilt stage and this rotational stage. The rotational stage allows us to get another degree of freedom in order to do another symmetrical analysis, except it has an accuracy which is well beyond what we really need in order to account for it. And a tip and tilt stage is used in order to accommodate any errors that might happen when we try to put the magnet into the holder. So if the magnet is slightly tilted offset, we can then retilt it via this system over here and account for any errors. And again, these mounts are also designed so that way they actually center the holder within the frame itself. So now that we have this design, we have our mechanical design and we have our magnet design, which the CLS actually quite likes. We're going to finalize the mechanical design, make it very nice and easy, and then provide the CLS with all the schematics and blueprints in order for them to manufacture it. And then once that's done, once they manufacture it, they're able to test it and compare it to our modeled results. Special thanks to all who have helped with this project, including our CLS, Adam, and others, and the machine department. Thank you.
Questions for Magjig?
Are there any other facilities besides synchrotron facilities that are interested in such a device?
Not that we know of. Not to the accuracy that we really need here. For most places, the only thing most of the places that use magnetic fields to this degree are usually located elsewhere in other synchrotrons, more or less.
What about other types of particle accelerators?
There aren't really that many others. I mean, for the most part, one of the other things is that the Hall probe is not the only method that can be used to detect magnetic fields. There are other actually more accurate sensors, but they are typically more costly, and the other accelerators that you're talking about usually have the funding in order to get those detector types.
So is the ring magnet made of multiple pieces that are put together? Or
No,
is it one?
it is one single magnet.
So do you know about the variation of the magnetic field generated by the ring magnet? Like is the material changing across the disk?
The material is assumed to be uniform. It's neodymium. It's a very strong magnet. Right now, we're assuming that everything's uniformly across. There is software that is able to actually calculate the domains within the magnet, but that takes a long time. It takes a while for it to simulate that, and we don't have access to that kind of.
Could you buy a piece of uniform neodymium? Like, do you know?
We're hoping that we can, but that's the biggest concern with our design. If it doesn't work, it'll be because that the magnet is, as you said, it's not ideal, so that we get some slight variation. So that's why we have 8 rotational stages in our mechanical system, so that you can check for that redundant.
And then you can average over it too, right?
Yeah.
Yeah.
So are there any specs you would have on the manufacture of the disc? Is there any way you'd be able to sort of specify to whoever's making it for you that it was of the appropriate quality that you need?
Are you talking about in terms of dimensions of the radius, or like more on what Adam?
Yeah, like the crystal structure and its ferromagnetic properties, and like, is there some I'm kind of thinking like the Webb telescope that's going through all the testing right now. Would your piece of magnet need to go through certain tests to meet your specifications, and what would those be?
Well, talking to our clients, we did find out that there isn't really a measure of, I guess, uniformity of magnetic material. But on the other hand, they did mention that when they do go into the testing stage, they would probably want to buy multiple magnets. So you would just buy, let's say, I mean, depends on the cost of the magnet, obviously, right? But with our previous configurations when we had the cube magnets, they were pretty cheap. So they said we'd buy, let's say, 100 of them, test them all, find which ones are, have the magnetizations that we want, and then go from there.
And if there's no other questions.
Oh,
or
I think there's one more
Sorry,
from
okay.
Thomas.
It seems that there are non-homogeneous can be the material. Would you be able to account for that in your measurement setup or procedure?
Potentially, yes. Again, as noted before, we use that by able to orient it in different orientations. We're able to average that out, and also with the tilt stage, we can adjust it in case there's any angular offs in the magnetization vector.
Okay, all right, thank you.
Oh, yeah.
One more, okay, one more.
Just being that it is like a ring, so it is a closed loop, do you have to worry about inductive effects skewing your Z-axis measurements at all or anything, or is CLS isolated enough that
Yeah.
it doesn't matter?
Yeah, it's all isolated. It's fine.